Hello everyone, I am Pratik Biswal, 19AE10023, Department of Aerospace Engineering, IIT Kharagpur. This video is a summation for the course Viscous Flow Theory, and in this video, I'm going to derive the Navier Stokes equation for an incompressible flow. And this is how the equation looks like. And these are the images of Claude Louis Navier and Sir George Stokes, who formulated this said equation. Earlier, to analyze the flows in fluid mechanics, there used to be the Euler equations, which used to look something like this. One thing that we can notice over here is it doesn't take into account the viscous forces. Like in this equation, there is a mu term that takes into consideration the viscous effects of the fluid. But in this equation, there is no such term that has mu or any viscosity related term. So this is not a very generic equation that can be used to model any kind of fluid. So it becomes not very useful in certain kind of flows and analysis. So this is why we need to study and obtain an equation that can be a little more generic, at least more generic than the Euler equations, and take into account the viscous effects in the fluid. So this is where the Navier-Stokes equation comes in, and it encompasses the viscous effects that are there in the fluid. But to get to this equation, we need to follow several steps. So the first step in that is deriving the stress tensor from the Cauchy construction. The two images that I've attached over here is Cauchy, that is the one who made this thing, and the Cauchy tetrahedron, that is the structure that is used to do this kind of analysis. And the tensor that as we know, is it relates to different kinds of vectors. Now, which two vectors it is relating over here, we will see it down the line and understand how this is useful. So before we get to the actual work that we are going to do in this step, there needs to be certain preliminaries that needs to be covered. So the first thing is the traction vector. What is the traction vector? Traction vector is the resultant of the normal stress component and the shear stress component. Officially it is defined as force by area or otherwise limit of F by delta S with delta S tending to 0. This can be considered as the vector analogous of stress because there is a normal stress over here, the sigma n, and there is the shear stress, that is the tau n, and we are taking a resultant of it and marking it as T of n. So that's all about traction vector. Now coming to the second thing, it is something known as the Cauchy reciprocal theorem or the Cauchy fundamental lemma. What it says is T of n is equals to minus T of minus n. What it is meaning is, let's say this is some kind of phase. The normal to this phase is say n cap, and this is another phase. Let's say the normal to this phase is exactly equal and opposite to n cap. That will be minus n. Now suppose the traction vector for this phase is, let's say, T of n, and for this phase let it be T1 of minus n. Now this is how both of them will get related. T of n will be equals to minus T1 of minus n, and it will not be even equal some other T1 or anything else. Both will be equal in magnitude. And this thing shouldn't also come as a surprise to us because this is nothing but the manifestation of Newton's third law of motion, according to which when two bodies interact, that is, in this case, two different phases, the forces that they exert on one another are equal in magnitude and opposite in direction, and hence even the traction vectors behave the similar way and follow the above relation. So the Cauchy stress tensor analysis that I'm going to talk in this part is useful even in solid mechanics. So it is a very generic thing and can be used either in solid mechanics by mechanical engineering people or in fluid mechanics or in aerodynamics also. But in this case, since I'm going to derive the Navier Stokes equation, let's consider only its applications for the fluid mechanics aspect. So this cube over here represents an infinitesimal element of some fluid, and the sigmas that are shown represent the stresses acting on each face of the fluid. Sigma 11 is the stress acting the face perpendicular to the one direction along the one direction. Sigma 12 is the stress acting on the face perpendicular to one direction along the two direction, and similarly the other terms mean the same way. But this analysis can be further simplified by reducing the structure, that is the changing this infinitesimally fluid element structure to something like this. This can be done by slicing this cube through a plane that is perpendicular to the n cap direction. Now another thing is, it doesn't really matter what shape of fluid element we're taking while doing this analysis, because it is really in the infinitesimal domain, that is the fluid element that we're assuming is really small, so it doesn't make any difference what kind of shape we're assuming. Now taking this tetrahedral shape into consideration, we'll carry on our analysis. So the tetrahedron I have drawn here, it has four faces like any other tetrahedron. This face that I'm marking with the laser has an area del A1. It has been shaded blue also. This face that I'm marking has the area del A2, and this face is of area delta A3. And this slanting face, now the one that I'm marking now, has an area of, let's say, delta A. There have also been shaded different. This is blue but not quite visible. So now let's proceed by analyzing the forces that are acting on this element. So we take the summation of the surface forces on this tetrahedron. Now I need to emphasize on this word surface, because the only force that will be significant in this case is the surface. And why is it so? I will show it later on. But as of now, let's just assume that we're taking into consideration only the surface forces. So the surface force comes like this: the traction vector for the face x1 and the area of the face x1, the traction vector for the face x2, sorry, this is x2, and the face and the area of x2, the traction vector for the face x3 and the area of x3, and also the traction vector of the face n and the area of n. Now I'd introduce the Cauchy reciprocal theorem. We can use it over here and convert the t of minus x1 to minus t of x1. Similarly, for the other terms, the same thing can be done, and we will end up with an equation that looks something like this. Not exactly equation, an expression. Now another relation that we can use is delta ai is equals to xi dot n delta I, which means that the projection of this face, the one that I'm marking, the slanted face, which has an area delta I, let's say on this x2 x3 plane, is equal to delta I1. So the projection of this face on a plane that is perpendicular to x1 is delta I1, and similarly for others. So we can say that the projection of delta I on a plane that is perpendicular to xi is delta I. So using this, we substitute the delta A expressions in this expression above and write it as minus t of x1 dot n delta A, and similarly for others. And when we take the delta A common, we end up with an expression that looks something like this: t of n, t of x1 dot n, minus t of x2 dot n, minus t of x3 dot n, whole into delta A. Now this for here is the net surface force. So let's just keep it like this and do the further analysis and get back to it when it is necessary. Now I told that I will show how only the surface force analysis is necessary in this case. Now coming to that step. Now let's analyze all the forces that are acting on the tetrahedron. The forces can be divided into two categories, that is body forces and the surface forces. Body forces are something that would be acting on the center of mass of the tetrahedron, and surface forces are something that would be acting on the surface of the tetrahedron, as the name suggests. So let's represent the body force with the symbol small b and the surface force with the symbol capital F of S, and the net force as small f. From Newton's second law, we know that the net force acting on a body can be represented as mass into acceleration. Putting that in the equation, we get ma is equals to b plus capital F of S. Now this m and the b terms are proportional to the volume of the tetrahedron. They're volume dependent terms. Now if we assume that the volume shrinks to 0, volume of the tetrahedron shrinks to 0, then we can easily ignore the body force and the net force and carry on with our analysis. And with that, the result will get that the net surface force will also have to be 0. So what we did is we did an order of magnitude analysis, assuming that the volume is extremely small, and that way this term on the left hand side and this term on the right hand side, that is the body force, they become 0 or else negligible. And from that we get this result that the net surface force is also 0. So what we get is the surface forces have to balance out each other. Now the expression that we had obtained before this one, the net surface force, we can easily equate this to be 0. That's what I've done over here. And now what we do is take components of this equation, and this is done in this way: t1 of n equals to t1 of x1 n1, that is x1 dot n is n1, t1 of x2 into n2, t1 of x3 into n3. This is not 2, this is 1, it is a writing mistake. And similarly for the second and the third components as well. Now in the next step what we do is t1 of x1, we replace this as, let's say, a symbol sigma 11, and this by a symbol sigma 12, and similarly for all other terms. As of now I am introducing sigma as just some constant that I'm using to replace this term, but later on I will say sigma is really good thing and significant also. So doing that, this is what we get: t1 of n is equal to sigma 11 n1 plus sigma 12 n2 plus sigma 13 n3, and similarly all the others. These three equations can be represented in a matrix form in this manner, having the T, the LHS, as a 3x1 matrix and the normal directions as a 3x1 matrix, and the sigma coefficients as a third order square matrix. And consolidating this even more, we can write it as this: it is the traction vector, the normal direction, and this matrix, let's say the sigma matrix as of now. So this sigma matrix that I'm calling till now is something that is the stress tensor. And this sigma 11, sigma 12, sigma 13 that I've written, and nothing but these things. This sigma 11, sigma 12, sigma 13, these are same. This sigma 11, sigma 12 are the same as these guys over here. Now writing this equation in an even compact form, what I get is T of n equals to sigma dot n. In this expression, T of n is a vector, n is also a vector, and sigma is a tensor that is relating this T, that is the traction vector, to the normal direction vector. And in Einstein notation, that is the index notation, we can write this as Ti of n equals to sigma ij of nj. Ti is a traction vector, n is the normal direction, and it is the stress tensor element. Now at the end of this, I'm introducing something that is known as the Cauchy law. Cauchy's law that states that if the body is in static equilibrium or A equals to 0, it can be demonstrated that the components of the Cauchy stress tensor at every material point satisfies the equilibrium equations. So what it states is, in this equation, put A equals to 0, and at every material point, that is, this volume of the tetrahedron shaped element has been shrunken to 0. That is, the volume has become negligible. So this one gets 0 because of A equals to 0 static equilibrium. B gets to 0 due to negligible volume. And that way also, we arrive at the same result, that the net surface force is 0 and the surface forces need to balance out each other. And from then on, this analysis is carried out, and the stress tensor elements would balance and satisfy the equation. Now that we have obtained the stress tensor equation, we can carry out the further analysis on that. The next task that is given is to show that the stress tensor is symmetric by moment balance. Initially, we might have done this step by taking a cuboidal element and the stress tensor elements in this manner that I already said before what the sigma 11, sigma 12 means. And let's say for instance we take this face, the one that I'm marking, and carry on the analysis on that. Sigma 12 is acting like this, sigma 21 is acting like this. Now a moment balance is done on it. Let's say some point at the center we take and do a moment balance. The expression that will end up with is a sigma 21 would be equal to sigma 12. That way, for when we do for all the faces, 6 faces, we'll get the expression that sigma ij is sigma ji, and they are equal. But here we have ended up doing it with a cuboidal shaped element, but it can be done in an even more generic manner, which I'm going to show now. So let's say this is the coordinate system, this is the some arbitrary kind of element. The P point that I've shown is some point on its surface. R is the position vector of that point from the origin, and dF is the surface force that is acting on it. The moment about point O due to force at P is equals to dm equals to R cross dF. Now to find the net moment, I have to integrate this expression over the entire surface. Now doing that, this is the expression that I get. Now we can express the cross product in index notation in this way, or the Einstein notation in this way. Epsilon ijk rj dfk. Rj and dfk are components of the vector r and df, and epsilon ijk is something that is known as the Levi-Civita symbol or the permutation tensor. How it works is, let's say if ij and k are cyclic, that is I would be 1, j would be 2, and k would be 3, or otherwise I would be 2, j would be 3, and k equal to 1. And similarly the third case also of 3, 1 and 2, then only this epsilon ijk would be 1. And if it is acyclic, that is let's say some 321,132, then the epsilon ijk would be negative. And in case the ijk have repeated elements, then it would be 0. It works in that way. And that is used to express the cross product in the index notation. And prior to this, what I've written is, prior to this, we have established that the only force that is significant is the surface force. So the dfk invariably becomes a surface force. We don't need to take all the forces to calculate the moment. So we can replace the dfk over here in terms of a traction vector. This epsilon ijk rj tk into dA. Now the traction vector can be expressed in terms of stress tensor, something that I established in the previous step itself. Now doing that too. This whole term, the sigma KL NL into dA, is what is the dfk. Now we'll use something that is known as a divergence theorem, which says that the surface integral of a vector P over a closed surface is equal to the volume integral of the divergence of P over the volume enclosed by that surface. Now we use that theorem, and this expression reduces to epsilon ijk del by del RL of Rj and sigma KL volume integral over the whole volume. Now for this term that I'm marking, we use the chain rule for the derivative and write it as epsilon ijk del Rj by del RL sigma KL plus Rj del sigma KL del RL into dV. Now this del Rj by del RL is like this delta J. That is, when J and L will be equal, it will be 1. Otherwise it will be 0, because Rj and RL won't be ever dependent on each other. They are just independent direction vectors. So we can write it as, okay, I missed a Kronecker delta over here. There needs to be this expression over here as well. Delta JL sigma kj. Okay, no, sorry, I haven't missed anything. This comes as delta JL into sigma KL. Now this delta JL, or the Kronecker delta, works like, if J and L are equal, then it will be 1, otherwise it will be 0. So that is what I've done here. Put L equals to J. So this expression becomes as sigma kj plus rj del sigma kl by del rl all multiplied into dv. And by doing an order of magnitude analysis over these two terms, when the volume is shrunken to infinitesimal sizes, we can establish that this first term would be clearly larger than this term, and this is negligible and comparable to this. So we neglect that because it is negligible, and reduce the expression to epsilon ijk sigma kj volume integral over the whole volume. Now we assume that there is no applied moment, or there is no internal moment in the fluid. That is, this LHS is 0. Now this is just an assumption that I've written over here, and there is no internal moment is a invalid thing to assume in case of, let's say, ferrofluids. In the case of that, there would be a different kind of stress tensor that we'll be getting. But okay, for now let's continue with the assumption that there is no applied moment and there are no internal moments. So by that way we can set the m to be 0, and the epsilon ijk sigma kj volume integral of that becomes 0. Now that we had begun with an arbitrary control volume of this shape, what we can say is the only way this integral can be 0 is when the integrand is 0, that is, the thing that is being integrated is 0. for all cases. So we get the expression that epsilon ijk sigma kj equals to 0. Now we expand this by putting different values for ijk, and we get as sigma 32 minus sigma 23 plus sigma 13 minus sigma 31 plus sigma 21 minus sigma 12. And hence we end up with the expression that sigma ij equals to sigma ji, which proves that the stress tensor is symmetric. Okay, so another thing that I would like to introduce over here is something that is called a void notation. This is useful in case of symmetric matrices. And since we have established that the stress tensor is symmetric, we can use it. What it does is, let's say there is some symmetric matrix and it has the element in this manner, sigma 11, sigma 12. And since it is symmetric, these elements would be equal, the elements that I'm marking. So what we do in that void notation is, we can simply write it as this: sigma tilde, sigma 11, sigma 22, sigma 33, sigma 12, sigma 23, sigma 31. So we have managed to reduce the tensor from 9 independent terms to just 6 independent terms. And this is a really nice achievement considering the analysis that we're going to do further. Now, the next step in this, we need to show that the stress tensor is isotropic for a fluid element at rest. Now, what is isotropic is, the matrix remains the same or is independent of any rotation in the axis. So let's see how we are going to do it. The stress tensor that I had obtained till now was sigma 11, sigma 12, sigma 13, sigma 12, sigma 22, sigma 23, sigma 13, sigma 23, sigma 33. We can notice it has been set to be symmetric, something that we obtained in the previous step. And the stress tensor as of now has 6 independent components. But this can be reduced even further. So let's see how. Here is a stress tensor or the element of a stress tensor given in a some kind of Cartesian axis. Now the axis gets rotated to a new system of x1 dash, x2 dash and x3 dash, and in that axis the stress tensor would change values. So this is the transformation of the axis to represent the stress tensor elements. And we can do this to our stress tensor too. And what is it? By transforming the Cartesian axis to such a system that even the diagonal components is 0, we can be able to write that sigma equals to sigma 11 dash 0 0 sigma 22 dash 0 and sigma 33 dash. So how this is done is, it is done through an eigenvalue problem by finding this principal values, and then we change this whole tensor to the basis vectors defined by the eigen vectors that we obtain from this matrix. Now that we have got a new expression for sigma, a very simple one, we can rewrite it as this: sigma ii by 3, sigma ii by 3 in the diagonals and all other components as 0. And when we subtract this matrix from this, we get a this matrix. Now these matrices do have a physical significance and names too, but I'll come to that later. Where sigma ii in this expression is nothing but the trace of the matrix, the stress tensor matrix. Now what we have done in this step is, we have split the stress tensor matrix into two different matrices, out of which one is an isotropic and one is a deviatoric. This over here is the isotropic matrix and it is independent of change in the coordinate system. And this is the deviatoric matrix which has non-equal principal components and it can change with change in the coordinate system. Now coming to what these components have effect on the fluid element. So let's say if the only effect that we're considering is of the isotropic. So this is a circular fluid element and if the only effect is of isotropic stresses, the forces would be acting like this. All inwards, equal in magnitude. Equal force in every direction. So in this way, the body would have no net deformation. And it can be considered to be fairly static. And if the only force that was acting is deviatory, the forces would act in this manner. And we can say that in this way it is getting compressed and in this way it is getting expanded. So this would be continuously deforming and it can't be really said to be at rest. And our initial purpose that we had begun with to show that the stress tensor is isotropic for a fluid element at rest. That is, fluid element at rest is what we need to consider. So if a deviatoric part acts on the fluid, it is not being at rest. So that would really not satisfy the purpose that we have begun with. So for that reason, this component needs to be out of the equation or else needs to be set as 0. The only components that can act on the fluid element is the isotropic one. And so the stress tensor has to be isotropic for a fluid at rest. And another thing is the isotropic component of the stress tensor that I discussed just above here is nothing but the hydrostatic pressure that we know. And the stress tensor gets an expression of sigma ij equals to P delta ij. Delta ij I had previously talked about, it is the Kronecker delta. And from the above analysis, we have known that sigma ij, that is, sigma ij is now isotropic stress tensor to be sigma ii by 3, this matrix over here. And this is the expression that we get from the hydrostatic pressure. So we can confidently say that P is nothing but minus 1 by 3 sigma ii. And this relation, all these, are valid only for a fluid element at rest and the sigma ij is isotropic. But for a general case, sigma ij, that is the stress tensor matrix, can be represented as minus P delta ij plus dij. Here, this is the isotropic component and this is the deviatoric component. Now for the next step, I need to derive the equations of motion for a fixed control volume. This fixed control volume is really a good approximation. So for that, I have assumed an arbitrarily shaped control volume that is fixed in space, not moving. It has a volume of V, a surface area of S, and I have shown the flow coming in and coming out in red arrows, and the normal vector to the surface through blue arrows. The red arrows over here can represent anything. It can be mass, momentum, or energy. But for our purpose over here, we only need to analyze the mass and the momentum. So let's begin with it. The first equation that I'm going to analyze is the conservation of the mass. Qualitatively speaking, it is can be said as the rate of change of mass of the control volume would be equal to the mass that is flowing in minus the mass that is flowing out. That is the net influx of the mass. And representing it quantitatively, a rho dv volume integral over the whole volume. And the time derivative of it, that is the rate of change of mass of the control volume, that is this, is equals to rho u dot n ds. Now this u dot n ds into rho successfully encompasses both the influx as well as the efflux. So how does it do it is, let's say for influx, u and n would be in opposite direction. You would be coming in and n is pointing outwards. So the dot product would result into a minus sign, and the minus with this would be a plus. So yeah, the mass flowing in gets a plus, and for the mass flowing out, u and n would be in same direction, and hence this negative would stay intact, and the mass flowing out would get a negative sign. So we can say that the quantitative relation means the same as the qualitative relation. Now when we take this term to the left hand side, we get this expression. Now this is what we call the integral form of the continuity equation. To get the differential form, we need to apply the divergence theorem, something that I had previously stated. Surface integral of a P is equals to the volume integral of the divergence of P. Now doing that thing, we can write it as del by del T of rho plus divergence of rho into U and the volume integral of that over the entire control volume is equals to 0. Now the only way this integral can be 0 is when this internal term is 0. Now we do that too. And by expanding this term by chain rule of derivatives, we end up with an expression like this. Okay, I missed a 0 over here. It will be a 0 equals to 0. And what we'll notice is this is nothing but the material derivative. Material derivative, or otherwise Lagrangian derivative, it is something that measures the change of a particular property over here, density, due to change in its position and change of time. It measures the change in a thing due to both temporal effects and convective effects. And it is really useful for flow processes, be it in fluid flow or be it in thermodynamics or anywhere else. And hence we obtain the continuity equation in its differential form over here. 1 by rho, capital D rho by dt, that is the material derivative, plus divergence of u equals to 0. This relation would be later on useful while we are analyzing the momentum conservation equation. Coming to the conservation of momentum, here we need to take into account two different effects. First is the Reynolds transport theorem. What it says is the rate of change of momentum of the control mass is equal to rate of change of momentum of the control volume plus the net efflux of momentum out of the control volume. And this is the link that I've attached to the Reynolds transport theorem page. If someone is interested, they can visit to this and read more about it. And from the Newton's second law that we know, the rate of change of momentum is equal to sum of all the forces acting on the body. Over here, all forces represents all the body forces and the surface forces. Now that I have established both of these expressions qualitatively, let's proceed on to write them quantitatively. The momentum of the control mass and the rate of its change. So rho u is integrated over the entire volume and it's d by dt. This is the temporal change of the momentum, and this is the convective change of the momentum. We can see this is momentum and it is flowing out and flowing in. U dot n will be positive for out and negative for in. And when we apply the divergence theorem to this expression changes to this divergence of rho u vector u vector. Now another thing that I would like to introduce over is this rho u vector is something that is known as the dyadic product of two vectors, and it is represented by this symbol that I've shown over here, a circle and a cross inside it. Now I expand this divergence by using the chain rule of derivatives and end up with an expression like this: rho u dv integrated over the volume d by dt equals to integration over volume of del rho u by del t plus u dot delta sorry, u dot nabla of rho u plus rho u into nabla dot u, or divergence of u. Now this over here is the material derivative of rho u. So we write it that way. Now we can expand this by the chain rule. And it changes to rho material derivative of u plus u into material derivative of rho. Now these two terms over here, it can be modified further and rearranged. We take the u vector common, and this changes to some expression like this. Now if we carefully analyze and observe, we can recognize that this is nothing but the continuity equation that I had obtained previously, this expression, and it is equals to 0. So that is something that we can do over there. We set this to 0 and we end up with a result that looks something like this. We can call this to be the result from the Reynolds transport theorem, or maybe call it some equation 1 or 2, anything as per convenience, but I would like to call this as a result from the Reynolds transport theorem. Now coming to the Newton's second law analysis. The rate of change of momentum is the sum of all the forces. So first I have taken the small f, that is the small specific body force or the force acting by unit mass. And then the surface forces over the entire surface. And previously I've established surface force can be established as a traction vector and multiplied it to corresponding area. And also the traction vector can be expressed as the stress tensor, the normal vector, and the surface area. So now that we have in this form sigma n cap dot ds, we can use the divergence theorem and write it as divergence of sigma ds. And what we have done over here is all the terms have been reduced to a volume integral, which will be helpful in finding the differential form. And let's name this as the result from Newton's second law of motion. Now the LHS of both these things are equal over here also and over here also. So we can set the RHS as equal to. Now we comparing the two results that we have obtained, we get as rho material derivative of u integrated over the entire volume is equals to rho specific body force integrated over the entire volume is equals to divergence of the stress tensor integrated over the entire volume. Now the only way this integral expression can be equal is only if the integrands also satisfy this equation. So hence we obtain the differential form, that is rho material derivative of u is equals to rho specific body force plus divergence of the stress tensor. Now dividing the entire expression by the density, we get this expression. Now this expression has a name and it is called Cauchy momentum equation. This describes a non-relativistic momentum transport in any continuum flow. For further reading about it, anyone can refer to this link over here. This notation I have expressed everything as the vector, and it is also justified. U over here is vector, F is vector, and sigma, which is a tensor, had been, as its divergence is being taken, so the rank has been reduced to a vector. So this whole equation is also okay in terms of rank. Now writing this in the Einstein or the index notation, dui by dt equals to fi plus 1 by rho del sigma ij del xj. Here I represents each and the one of the three components of all of these things. So this is the equation of motion by assuming a fixed control volume. Now for the further steps, obtaining an expression for the stress tensor in terms of the velocity gradient, assuming the fluid to be isotropic. Okay, the equation that I have obtained till now looks something like this. Material derivative of ui equals to fi plus 1 by rho divergence of sigma ij. But what exactly this term is? How are we going to simplify this even more? Well, we can choose to leave it like this as Cauchy did, or else maybe try simplifying it. So we are going to try to simplify it, something that has been previously done, and I'll be repeating that same way. So this can be done by the constitutive relationship. Now, what is a constitutive relationship? It is a relation between a dynamic quantity and a kinematic quantity. Okay, so that being said, previously we have known that sigma ij equals to minus p delta ij plus dij, where this is the isotropic component and this is the deviatory component. And the deviatory component can also be expressed as dij equals to cijkl del uk del xl. Here dijk is the deviatory part and is a second order tensor. This is the strain rate tensor, and this is the fourth order tensor. Cijkl any fourth order tensor, and we will analyze it further. Now over here I have found the entire strain rate tensor and made an effort to get an insight into why this relation is justified. So this is the strain rate tensor as we know, and this is a matrix, a 3 into 3 matrix, and as we know any random matrix can be split into a symmetric and an antisymmetric part. So we do the same over here. Took the symmetric part by half of del u plus nabla u plus nabla u transpose, and antisymmetric part by taking the minus. And further, the symmetric part that we have obtained over here, it can be split into an isotropic matrix and a symmetric trace matrix. Symmetric trace matrix is a symmetric matrix with a trace of 0. So we do that too, and below I have mentioned how these matrices would look like. Now, this decomposition of the strain rate matrix would be useful later on, and it also gives an insight that this strain rate is indeed related to the stress tensor, because the strain rate stress tensor can also be decomposed similarly into an isotropic and a deviatory part. So now let's get back to the constitutive relationship, that is this. Now how to find this Cijkl that I have shown over here. This can be done by assuming that the fluid is statically isotropic. What it means that the deviatory stress generated in an element of the fluid by the velocity gradient would be independent of the orientation of the body element. This assumption is also justified because almost all of the fluids that we know are isotropic. Okay, careful on this. Almost all fluids, not all fluids. So now proceeding further, Cijkl is a fourth order isotropic tensor, something that we have assumed it to be. And as we know, Kronecker delta is a second order isotropic tensor. So we can write that Cijkl equals to lambda delta ij delta kl mu delta ik delta jl plus gamma delta il delta jk. Here lambda, mu and gamma are just arbitrary constants, as of now at least. Later I will establish they do have some physical meanings and names. And this expression written over here is a linear combination of all fourth order isotropic tensors represented through the deltas. And this is a generic expression for the fourth order isotropic tensor. Now what we do is we apply the properties to this expression, apply the properties of the Cijkl to this expression and try to evaluate what these constants can be. The first thing that we apply is Dij is symmetric, and that way Cijkl should also be symmetric.Cijkl is symmetric means Cijkl will be equal to Cjikl. Now in this expression, everywhere that I occurs, we have to replace it with j, and replace everywhere that j occurs with I. Now doing that, we can end up with an expression like this. And when we subtract this one from this one, or even the other way around, what we'll end up with is mu minus gamma delta ik delta jl minus delta jk delta il equals to 0. Cjikl and Cijkl will be equal. So subtracting them would yield 0. Now these terms get subtracted and we end up with an expression like this. Now this term won't be always 0. This delta, one with the deltas, won't be always 0. Let's for example, if I is 1, k is 1, j is 2, l is 2, this part before the minus will be 1, but this one over here would be 0. So this expression is not actually getting to 0. It is becoming 1. So the only way this equation will hold true is if mu equals to gamma. Now we add that simplification to the generic expression for the Cijkl and write it as this: Cijkl equals to lambda delta ij delta kl plus mu whole multiplied to delta ik delta jl plus delta il delta jk. Now substitute this expression into the constitutive relationship. Dij equals to this whole Cijkl expression multiplied into the stranded tensor. Now we expand this term by term and get three different terms. Dij equals to lambda delta ij delta kl del uk del xl then plus mu delta ik delta jl del uk del xl plus delta l delta jk del uk del xl. Now we apply the property of the Kronecker delta. We know that this delta kl would survive only if k equals to l. So we apply that, and over here it survives if I equals to k and j equals to l, and in this if I equals to l and j equals to k. So on doing that, we get that dij equals to delta ij lambda del uk del xk plus mu del ui del xj plus del uj del xi. On careful observation, we can see that this term, this del uk del xk, is nothing but the divergence, and this term over here is nothing but the symmetric part of the stranded tensor. And another thing, this is the second constant that we are going to apply other than the symmetric. What is it? That the Dij is a symmetric trace matrix. That is, this is symmetric matrix and its trace is 0. So the trace of that thing would be 0. Now to find the trace, we have to replace j with I for all the terms. Now let's do that. Delta ii lambda del uk del xk plus 2 mu del ui del xi. If we replace j with I, both of these terms become equal, and we can write it as 2 into del ui del xi. Now since this both the del uk by del xk and del ui by del xi are divergences, we can cancel them out, and this delta ii, the Kronecker delta ii, would be 3. So this expression reduces to 3 lambda plus 2 mu equals to 0, and lambda is equals to minus 2 mu by 3. This mu is nothing but the dynamic viscosity that we know previously, and it occurs in several expressions too. This lambda is the second coefficient of viscosity, or otherwise known as the bulk viscosity. It comes into play in the stress tensor in cases where the fluid is divergence free, that is, it is not incompressible. So now we put these values of lambda into the expression for the Dij and end up with an expression that looks like Dijk equals to 2 mu half of del ui del xj plus del uj del xi minus 1/3 of delta ij del uk del xk. So this is the final form of the constitutive relationship, and when we substitute this in the stress tensor expression, that is this expression sigma ij minus p delta ij plus tij, we end up with an expression that is like this. So we have successfully managed to show the stress tensor in terms of velocity gradients. Now moving on to the next step, substituting the expression for the stress tensor in terms of velocity gradient into the equations of motion to obtain the Navier Stokes equation. From previous analysis, I have established that del ui by del t, that is the material derivative of ui, equals to specific body force plus 1 by rho divergence of the stress tensor, that is the Cauchy momentum equation. And in the previous step, I just proved this expression. Now when I substitute this delta ij in this equation, it becomes like this. Now I take this del by del xj of each term by term. For the first term, this is the p term, we have a Kronecker delta ij. Then the only point when it survives is, that is, it doesn't get to 0, is when I equals to j. So we do that, and it becomes minus del p by del xi, the partial derivative of p with respect to an xi component. Now moving on to the second component, second term. There are actually two terms over here, but in a whole it is the second term. Now del by del xj of that, okay, I will be expanding it further in the next step. And then del by del xj of this last term over here. Now I expand these two terms, del ui by del xj and del by del xj. So del square ui by del xj square, and del by del xj of this term ends up with del square uj del xj by del xi minus 2/3 of del square ui by del xj del xi. What I have done over here is del uk by del xk was divergence. So it doesn't matter if it is k or I. So I've replaced k with I, and sigma ij survives only when I equals to j. That is also done. And we end up with this expression, del square ui by del xj del xi. And this over here is something that's called the Navier Stokes equation, without any approximations regarding the compressibility of the fluid as of now. It is material derivative of ui equals to minus 1 by rho del p by del xi plus mu by rho. This becomes something known as the kinematic viscosity, represented by the symbol nu, del square ui by del xj square plus 1/3 of del square uj del xj del xi, and finally the specific body force. The approximation that we have taken as of now is the fluid is isotropic. We have applied no moment and there is no internal moment, something that was used to prove the tensor to be symmetric. Now all the fields of interest, such as the pressure, velocity and density, are differentiable, otherwise this derivatives that we are doing over here would not have been possible in the first place. And the flow is continuous. Now proceeding on to the final simplification is the Navier Stokes, simplifying the Navier Stokes equation for an incompressible flow. From the continuity equation, I have established that for an incompressible flow, the divergence of the velocity field would be 0. That thing will be useful over here. So from previous analysis, the stress tensor, the general expression for the stress tensor has been obtained to be of this manner. Now from the continuity equation, we get this expression that for an incompressible fluid, the divergence of the velocity field would be 0. That way this del uk by del xk becomes 0. And the stress tensor now reduces to be of just 3 terms, whereas it was previously of 4 terms. And even that these 2's get cancelled, and we end up with an expression for sigma ij in this way. Then this is the Cauchy momentum equation. And when we put the sigma ij into this equation looks something like this. and taking the del by del xj of each and every term, we get like this, and then the specific body force over here. Now we need to analyze these two terms that we have obtained. The first is the del square ui by del xj square. So what it is we put the indices for the j. Del square ui by del x1 square, del square ui by del x2 square, plus del square ui by del x3 square. It is nothing but nabla square of ui. Now the second term, del square uj by del xj del xi. We can also write this as del square uj by del xi del xj, because it doesn't really matter in what order we take the partial derivative. Now this can be written as del by del xi of del uj and del xj. Now this is the divergence term, and divergence is equals to 0 for an incompressible fluid. So this gets to 0, and hence this term gets to 0. Now the only term that gets left behind is this. So yeah, now the Navier Stokes equation is finally ready. So finally, we obtain that the material derivative of ui is equals to minus 1 by rho del p by del xi plus nu del square ui by del xj square plus fi. This is the Navier Stokes equation in the index notation for an incompressible fluid. And when we write it in vector form, it looks something like this. The ui changes to u vector. This becomes grad of p. This becomes the u vector, and becomes the specific body force vector. Now, what are the assumptions that I've taken? Here I say same as all before, which means that the fluid is isotropic, no internal moments, the fields of interest are differentiable, the flow is continuum. And for that step, the additional approximation is the incompressible fluid. And so we have successfully managed to derive the Navier Stokes equation in its entirety. This equation encompasses the viscous effects of the fluid with this term, but still it can't be really said to be generic due to all these approximations that we have taken. But this equation is fairly valid for almost all of the cases that we are going to meet. Let's say be it the Hagen-Poiseuille flow or the Couette flow or any practical problem that we can model on the basis of this equation also. So in a sense, this is a really useful equation and comparatively more useful than the Euler equations. So with this being said, I've come to an end of this video as we have derived the Navier Stokes equation with all the steps covered. So yeah, that's all. Thank you for the paying attention, and this video has come to an end.